Hey there and welcome to the VEX and VOPS Houdini tutorial from Line Between. Now this tutorial is drawing comparisons between VEX and VOPS, explaining what each one is, explaining how they're used, and then we're going to create a setup in both and show you exactly how those two are similar and how they're different, so that you can get a feel for whether you want to approach Houdini from the angle of VEX or whether you want to approach it from the angle of VOPS. So, a good starting point would be, what is VEX? Well, VEX stands for Vector Expression Language. It's the coding language used in Houdini. Now, a coding language is just the way to communicate with a computer. Think of it like this. If you have a neighbor who doesn't speak English, they speak their own language, say they are Spanish, you would need to learn Spanish to communicate with them. Much like with the computer, you have to learn the computer's language to communicate with it. So VEX is Houdini's computer language, right? It's its coding language. And we can tell Houdini to do certain things using that language. Now, VOPS stands for Vector Operators. Now you can already see how those two are linked. VEX is a vector expression language. VOPS, vector operators, right? So VOPS are basically little chunks of VEX code packaged as nodes. So VOPS would be the node-based way of doing all the things that you would do in VEX, which means that VEX and VOPS are interchangeable. They're the same thing, more or less, in different forms. And to really understand this, we can go ahead and open up Houdini. So in Houdini, I'm going to go ahead and drop down a geometry node, and I'll just call this whatever, VEX VOP comparison. We go inside here, and we can drop down an attribute VOP. So now that we have an attribute VOP, you'll notice it has some inputs. Now, we don't have anything for it to run over. Usually it would run over some points or primitives, and inside of the VOP you would change things like color or an attribute or whatever it may be. We don't have that, so we're changing this to detail. That means it just runs as a standalone node, or it doesn't affect inputs, it's just affecting detail. So dive inside here, and you'll see that by default, it gives you these two nodes over here. These are global variables. These are things that you can bring in, like the position in space. So if you were bringing in points as opposed to running over detail, you would have access to all of this information from your points. So the P value, that's your position, the velocity, force, age, life, all of that, right? But we don't need this, we're running over detail, so you can delete that. What we are going to do is create two constants. We're just going to take two numbers, right, X and Y, multiply them together and output the product. What does that look like? Well, we have a constant, we can give it a name, we can call it X. It also has a type. In this case, it's float, and a float is just a number that has decimal places. So it could be 1.1, 1.2, 5.6, whatever it is, right? And to understand this better, in contrast to an integer, we can test out a float of 3.2, and then try changing this to integer. It's not happy with 3.2. It just sets it to 3, right? It has to be a whole number. So we can set this back to a float, make this 3. We can also drop another constant right over here, call this one Y, make it 2. Then we can multiply these together, because remember we wanted to multiply them and get the product. So we multiply them together, we can just call this X times Y, and then we can create a bind export over here, which binds it to an attribute. So you put this into the input, and then you can call this something like product. So it goes 3 times 2 and gives you a product. If we go up a level, we can actually take a look in our geometry spreadsheet. We should have a detail attribute called product, which gives us 6. Expected, nothing crazy. Now, if we go and create an attribute wrangle, so just type attribute wrangle or AW for short, you'll notice, firstly, we also have 4 inputs. We also have run over points, which we can change to detail as well, and then set our display flag on here. In here, we can do the exact same thing. We can say float x equals 3, and then we put a semicolon. That's like a full stop, right? It's saying this is one piece of code. This is one thing to execute. Then you can move on to the next thing. New sentence, basically. Float y equals 2, semicolon. And now we can do something like at product equals x times y, semicolon. Now this at syntax is just telling Houdini that this is an attribute. If that attribute existed before, it will adjust the attribute. If it didn't exist, it will create a new one. So we're just saying create an attribute called product equal to x times y. And if we go over to our geometry spreadsheet on our attribute wrangle, we also have this. So as you can see, these are two ways of doing the exact same thing. And now you may not exactly be able to draw any sort of concrete conclusions from this or any sort of preferences, because this was very basic, right? We were just working with some numbers. So let's actually create something. Let's create some spirals, right? We'll create some points and turn it into a spiral, and that spiral can be controlled with a few parameters. That would be a cool thing to do, and it would be somewhat intermediate. So let's remove these two nodes, and let's give this a go. So this time, I'm actually going to start with an attribute wrangle. So let's drop down AW, attribute wrangle. Put it down there. Once again, we're not going to be working with any input, so you can just change this to a detail. Over here in your VEX expression editor, you can hold Alt+E to bring up this little box, and this just gives you some more space to type, right? So that's pretty nice. First thing we're going to do is we're going to define how many points we want in our spiral. So let's say int points, right? We're just making a variable. You can think of it like that constant we had earlier. But this time, we're going to make it equal to channel integer. And that channel integer is going to be called points. And I'll show you shortly exactly what creating a channel integer looks like. But this that we're doing over here is just creating a function. So anything that's this color, the sort of teal color, is a function. So this function is the channel integer function. It does a bunch of code behind the scenes that you can't really see. Next, we can also create an angle. And this is the angle between each point. So float angle equals channel float this time, so CHF. And we can just call this one angle. I'm just going to show you what this looks like. We can apply and accept. And it won't do anything yet because we have to actually tell Houdini to look for these channel references. So go over here and say create spare parameters. And down at the bottom, we now have points and angle, and we can adjust these to whatever we want. So we can set this to like 0.1 and 100. Back in here, Alt+E, bring this back up. So we're going to create something called float R. And we're just initializing it for now. So initializing just means we're creating it to be used later. We can also create another float called float theta and two more floats, float x and float y. And you can separate your two with a comma, which is quite a nice little thing that you can do. And you can make those two equal to 0. Now we can also initialize a position because we need to be putting these points at a certain position that we don't know yet. So we'll be creating it later, but for now we can make something called vector pos, which is equal to 0, 0, 0. It's a 3-component vector. You can just easily put it like that. Now we need to create a for loop because we need to run over each point and decide where that point needs to be placed and then place it. So we say for, and then in here we create an integer called I, which is to start with equal to 1. Then we say as long as I is less than the total number of points we have, then do the following. And each time we've completed doing the following, increment I up. So that means increase I so that it runs again until this condition over here is met. So the first thing we're going to do is adjust our R value. So R will equal 2 times pi, and you can do $pi, times I divided by points. Now, I wouldn't say worry about this too much. This is just basically for creating a spiral. This is a bit of an equation that I had to recently figure out. So don't worry about it too much. This isn't really the point of the tutorial. The point of this tutorial is Vex versus VOPS. I'm just trying to explain it so you can at least follow along. We then have theta. So we want to make theta equal to angle times I. Now remember, I increments up each time this code is run. So for the first point, I will equal 1. For the second point, I will equal 2. For the third point, 3, fourth point, 4, and so on and so forth, right? And so by having this, you have evolving values. Each time I is incremented up, these values will change to adjust. And then we can just make x equal to r times the cosine of theta. We can make y equal to r times sine of theta. And this is generally how you'd make a circle. You would have cosine of a value and sine of the same value driving x and y, and that will make a circle on a single plane if it's run over a full period. Next, we say pos equals set. So this is a function. Once again, x comma y comma 0. And then the last thing to do is to add a point at that position. So we say add point 0 comma pos. And if we apply and accept, what you'll notice is that we've created a spiral of points. And there should be 100 points. And if we middle mouse on our attribute wrangle, you'll see points 99. And that's because we're starting at I equals 1. You could change that to I equals 0. 100 points. Okay, no problem there. Okay, so we have this. And if we increase our points, it spirals out. And if we decrease them, it comes closer in. Right, so pretty cool. We can set this to just 100 points. And now, the moment that we've all been waiting for. And you do the exact same thing in VOPS. Because right now, all of this code might seem very confusing to you, and this isn't very intuitive because you don't like code, or you might not have coded in the past, whatever it may be. And you would rather do this in VOPS. You would rather do this with nodes. It's very much possible. So let's create an attribute VOP over here. Once again, we're going to run over detail. So we can switch our display flag over to this attribute VOP and dive inside. Remember, we don't need these, so we can delete these. So what did we start with before? Well, we started with the number of points that we need. So what we're going to do is create a parameter this time for the number of points. So the name of this parameter will be points, and it will be an integer, right? Remember, we made a channel integer for points. And so this has done the same thing now. And the label for this can also just be points. Then we also needed an angle. So we create another parameter. And we call this one angle. Give it a label called angle. And this one will be a float, so that's fine. So we've got our two parameters, and they show up over here. So we can put 100 points and an angle of 0.1. And now these two values match up, and we're good to go. So we first did some maths. We calculated our r value. So let's do that quickly. R was equal to 2 times pi. So we can quickly figure out what pi is. Let's use a trigonometric function, set this to arc cosine, and arc cosine is equal to pi at -1. And the reason I know that is because I Googled. It's not because I'm good at maths. Don't worry, a lot of this isn't because I'm good at maths. It is because I just search these things. So pi, right, we get pi from that. That's cool. We then want to do multiply it. So we can drop a multiply constant. So we plug that in, and we want to do multiply it by 2. So this gives us 2 pi, and we can call it that. We can then create a null over here and call it r, so that we know that this is r over here. And the output name we can also call r, right? So it's easier to work with. So now we have points, angle, as well as our r value. And we can just line these up over here. And isn't this starting to look a lot like this VEX code? We have points, angle, r. So now we can also create our theta value. Now, our theta value was actually created inside of a for loop. So we need to create a for loop. So let's create a for loop. And the way a for loop works is however many inputs are given to it, it will run over whatever nodes are inside of it until it has completed it the number of times as the input requests. So if we plug points into the length index, then it will run this the number of times that we have points. And so we can actually just add a point in here. And if we plug length out into the handle, and then ptnum into out, what ends up happening is we generate a point for each of the number of points that we're putting in. So what does this look like? If we go up a level and we middle mouse on this, we now have 100 points being generated, because what it's doing is it's taking this value over here and generating points. So cool, we have that, but all of our points are just placed right over there at the origin because they don't have a position. So how did we calculate position? Well, we had to do some maths to figure out x and y, so we can do that again. So the first thing we'll calculate is our theta value, and what we'll do is we'll convert this integer to a float, so we'll do int to float. So this int to float will take the index out. This is the equivalent of that I value that we had, where we said int I equals 0, I less than points, I plus plus. Every time it runs over this, this index value will increase. So that means we can treat this as that I value. Next, we can drop a multiplier, because remember we multiplied this by our angle. So we multiply this by our angle, and that's actually the reason why we use this int to float, because these nodes assume that the output is the same type as the first input. So if we didn't change this to a float, and then we multiplied this by our angle, it would have given us an integer, because this was an integer coming in. So that's just a little thing to take note of, but nothing too complicated. So what that actually gives us is theta. So we can put this over here, plug this in, call this theta. So we've used a null to hold the value, and we've called it theta, and we can also just change the output name to theta, so now it outputs theta. And so what did we do with theta? Well, we use that for a sine and cosine value, so we can drop a sine graph over here and a cosine graph below it. And this will let us calculate what exactly? Well, cosine was for x, and sine was for y. So you plug theta into x, theta into y, and then we want to put that to position. But before we do that, we have to multiply this by r. But if you take a look back, our r value first needs to be multiplied by I divided by points. So we can do that very easily. We firstly need to divide. So we divide I by the number of points that we have. So I over 500. And then we multiply that with our r value. So r times that. And then the last thing that we do with that is we multiply our x with r, and we also multiply our y with r. That gives us our final x and y values. And then all we need to do is do a float to vector. Float to vector will take these two values that we have and convert it to a vector. So component 1 would be x, component 2 would be y, and then component 3 we can leave as 0. And if we plug that into our position for our add points, it should work, but it's not. And yeah, that's that int to float thing that tripped us up a little bit earlier. Switch that int to float into your divide 1, input 1, and after all of that, we have a spiral. And it's the exact same spiral as our attribute wrangle. So you can compare these two, and each one of them has these values that we can now control. And so each one is exactly the same. So after all of that, we now have a strong understanding of VEX compared to VOPS. Now, in my opinion, this is very easy and clean. And VOPS can get a bit messy and complicated. Of course, you could press Ctrl B, lay it out nicely with L, and then everything looks a bit easier to read, and it's not such a mess, right? And that's fair. And if that's your thing, then go for it. I have no issue with that. And you'll get along just fine in Houdini. But do keep in mind that when your setups start to get complex with VOPS, they can start to get really complex. These 15 lines or so of code as opposed to these nodes. I find this easier, but that's just personal preference. So what could you do with this? Well, let's just turn it into something interesting. If you drop an add node and add it by group, and then duplicate it over by holding Alt, you can have these two. You can merge them together. Maybe the one should have more points, that it spirals more. You can also give this one more points, something like that. That looks kind of cool. And then maybe two different poly wires. One over here, click and drag over, one over there. Each one with 5 divisions. And And then you could maybe do a wire radius of 0.05 on the smaller one. You can give the thicker one a color maybe. So let's make the thicker one a blue. And subdivide. More faces. Attribute blur. And we'll do it by proximity, so that gives us some interesting shapes. And then just do maybe a bend node or something. With a capture of 1 and -5. And then we just increase the points even more on these to 500 and 700. What we can do is just put the camera, an environment light, give it an HDRI, maybe put an area light over here. And so this is just so that, you actually have something to show for following along with this, because this was really just to give you an idea of the comparison. So with all of that, you can very easily just drag over a gold shader and you'll end up with something interesting. So yeah, I hope that this helped you understand how attribute wrangles and attribute VOPs are pretty much the exact same thing. Really, it's a good idea to understand both. Attribute VOPs are a lot better for noises. Like, I don't think I've actually ever created noises in an attribute wrangle, but I do it all the time in an attribute VOP. Likewise, I don't think I've ever done anything heavily mathematically based in an attribute VOP, just because I find it easier and more intuitive in VEX and easier to follow with. And so, yeah, I know some of the best Houdini artists actually just use VOPs, like Simon Holmedal from Panoply, who used to work at Man vs. Machine. He uses attribute VOPs and his work is insane. So don't think that this is like a simplified method or a dumbed down version of coding. It's not at all. It's very much an equal and it has its benefits. So you just need to weigh it up for yourself. So I hope that helped you, and you can get away with using either one. So knock yourself out, have some fun. And I hope you enjoyed this tutorial. This was a bit of a different style, so let me know what you think. And finally, just before we say goodbye, thank you to all of our patrons. Thank you for watching, and I'll see you next time. Bye.